All right, good morning. It's time for us to start. How are we doing? How'd the exam go? All right. All right, you guys, if we could give me your attention, I'm an attention hog, I guess. All right, so very quickly, exam 2 is going to be coming up in a few weeks. When do you want to start studying? Yesterday, yes. That was the correct answer, yesterday. All right, so just some details. So on Friday, Brian will be handing back the exam, letting you and going over any questions you might have, going over the key, and then he's going to recollect them. And this is really, really important, all right? The exams in this class are secure. So you can look at them, but you have to turn them back in. You can't make digital copies of them, so you can't photograph them. You can't take notes on what's on the exams, all right? And then there's a deadline for requesting a regrade. That's 2 weeks from yesterday, okay? All right, and if you don't come to class on Friday, then you can visit with me or the TAs during office hours. If you violate any of the above, that's academic misconduct, okay? All right, any questions about that? All right. The other thing I wanted to just point out is that starting on Thursday, once the exam's been scored, there's going to be a quiz that shows up on Canvas. It's basically asking you to do a quick self-assessment. All right, so it's asking how the exam went for you, what you prepared for the exam that worked, what you did in prepping for the exam that did not work, and what you'll do differently for exam 2. All right, so this is required for everybody, and the deadline will be the Tuesday the 20th. All right, and in order to get full credit, you have to answer all the questions, and you need to do it thoughtfully. All right, any questions about that? Okay, so the last time we met, we've been looking at system and particle partition functions. So we've pointed out that the system partition function is equal to our particle or molecular partition function raised to the n power over n factorial, where n's the number of particles. Using this relationship along with explicit functions for those particle partition functions, we were able to determine the energy that we expect to observe, all right, macroscopically. We saw for a monoideal gas, 3/2 RT, we've related that to translational energies or average kinetic energy of particles in the system. We looked at a more complicated case, the diatomic ideal gas. For the diatomic ideal gas, we get a contribution to the energy from translation. So it's exactly the same as the translation or kinetic energies that are associated with monoatomic ideal gases. Because it's a linear molecule, we also have rotational contribution, that's RT. And then we have a vibrational contribution, the 0-point vibrational energy, and then energy above the 0 point. Right? So some questions that we're going to do today. We're going to extend our discussion of applications of partition functions. So we're going to see, can we determine what the heat capacity is? All right. What we're going to see along those lines is that with the heat capacity, and we'll define what heat capacity is in a moment, there's going to be a translational contribution to it, possibly a rotational and a vibrational contribution. Okay. All right. And then from there, we're going to ask, can we calculate the pressure from the partition coefficient? And then we've been using this expression, system partition function, related to the particle or molecular partition function. And what I want to do is show where that comes from and talk about when we use the two different forms. Okay? All right, before we move forward, a couple things that I want to do. Where do we have that? All right, so one thing I want to do is talk about heat capacities. So here what I want to do is back up a second and say, if I have a system, the change in the energy of that system, right? So you've seen it as delta U or delta E, is given by energy transferred in or out of the system. And there's only two ways to transfer energy in or out of a system. Can somebody tell me what they are? Heat and work. All right, that's candy worthy. There you go. Let's hope your interview questions go as well. Right? Q plus W. Okay? All right, the other thing that we can say is that if I choose to hold my system's volume constant, that means I don't let my system expand or contract. And that means that if I'm looking at work due to expansion or compression, that'll be equal to 0. All right, you can help yourself to candy too. All right, so at constant volume, delta U equals QV. Okay? All right, so this says that if I have no work transfer occurring, then the change in the energy in my system is due to heat added or removed. Okay? All right, and then, back from Gen Chem and probably middle school, you know that heat capacity relates the temperature change of our system to the heat added, right? You've seen that before, okay? Now, if I add to this saying I'm doing this at constant volume, right, that tells me that the heat capacity can be equated to Q sub V over delta T. All right? And if I'm holding the volume constant, that also tells me this heat transfer is the change in the energy of the system in its entirety. So that's equal to delta U over delta T. Okay? Does that make sense? All right, so in this sense, that says that the heat capacity relates the energy change in the system due to a change in the temperature. Right? And we're going to be building on that today. Okay? All right, the other thing that I wanted to do at the outset was just remind everybody from back in chapter 1, energy levels for translation, vibration, and rotation were given by these equations. And so we will use these in the next chapter to calculate partition functions. But for now, when you see a partition function that's got h squared and 8m in it, and a volume, that suggests that that partition function is due to the translational energies. If I have one that has the moment of inertia showing up in it, that's associated with rotations. And when I have h nu, where nu is the fundamental frequency in it, that tells me that that's related to the frequency, the vibrational energies. Okay? All right, the other thing that we didn't have time for last time, and I just wanted to do this very quickly, and that was this derivative of the natural log of 1 minus the exponential. So this is going to be the derivative of the natural log of 1 minus e to the minus beta h nu. And we're taking the derivative with respect to beta, and we're holding n and v constant. Okay? So I have the derivative of a function of beta. So we know that the derivative of the natural log of a function of beta. So we know that's going to be equal to 1 over that function. Okay? And then I have to take a derivative of that function with respect to beta. Well, the derivative of 1 with respect to beta is 0, but the derivative of the exponential is going to be the exponential back, all right? So that means I'm going to have minus e to the minus beta h nu, all right? And because this is an exponential of a function of beta, I have to take the derivative of that with respect to beta, all right? And the result of that next derivative gives me minus h nu, okay? And then if you put that all together, you get a positive value and that term. Does that make sense? Okay? All right, we're going to be using that derivative again today in a little bit. Okay? All right, so the last time we met, we talked about the diatomic molecule and the energy of our system. And we basically said that for a diatomic ideal gas, the energy of the system can be described in terms of translation, rotation, vibration, where that's the 0 point vibrational energy, and that's the vibrational energy above the 0 point. So I'm going to write that out explicitly. That means U of translation plus U of rotation plus U 0 point vibration plus U of vibration. Okay? All right, so in the next section, what we want to do is talk about heat capacity. So this will be heat capacity at constant volume, CV. Okay? And here I'm going to formally define the constant volume heat capacity. That's going to be the derivative of the energy of the system with respect to temperature, holding V and the number of particles constant. Okay? All right, and this is why at the outset I derived the equation, said heat capacity is delta U over delta T. So this is just now leading to the formal definition. Okay? And then putting this together with what we've introduced previously, we know that that energy of our system, this U means the experimentally macroscopic observation, we expect that to be the same as the average energy of our ensemble that we calculate. Okay? All right. And then I just want to take a moment to talk qualitatively about what that definition means. All right? So this is really, the heat capacity relates the change in system energy so delta U to a change in temperature. Under the experimental conditions where I'm holding the volume constant. Okay? Some of the homework's not the one that's due this Friday, but next Friday. The homework next Friday will basically be looking at the change in the energy of the system due to a change in temperature. And one of the things that you'll see is that as you change the temperature, well, that's going to influence the kinetic energy of the particles. That's going to influence the rotations of the particles and the vibrations. Okay? All right, and then just to apply this a little bit, well, what we saw previously for a monoatomic ideal gas is that the energy of the system was 3/2 RT per mole. So there's our molar energy, right? And then if I want to take that information and determine the heat capacity, it's straightforward. That's going to be the partial derivative of that average energy of our ensemble with respect to T, holding V and N constant. And if I take the derivative of 3/2 RT with respect to T, what do I have left? I have 3/2 R. Okay? All right, so for a monoatomic ideal gas, if we're holding the volume constant, we expect this to relate the energy change of our system to that temperature change. Okay? Right? And there's something interesting to point out here. Right? Is temperature in this? No. So this is independent of temperature. We'll see in chapter 5 that becomes important. Okay? All right, and we can do the same thing for a diatomic gas, right? So translation, rotation, 0 point vibrational level, or vibrational energy, and then this is my vibrational energy above the 0 point. If I want to take this information and calculate the heat capacity, I just need to take the derivative of this whole thing with respect to T, and that's what we're going to do. All right, so that first term goes to 3/2 R. That next term, the derivative of RT with respect to T, gives us R. Right? The derivative of NH nu over 2 with respect to T will be equal to what value? It's going to be 0 because I have no temperature in there. Right? That's a 0 point. It's a reference. Okay? Right? And then we have the derivative of this mess. All right? So I don't want to do it explicitly in here. You can follow through it. All right? I just wanted to make sure that every step is shown. Right? But I will talk about the highlights of the derivation. So one of the things that we see is that this is in terms of beta. So if I want to know the derivative with respect to T, then I'm going to have to take the derivative with respect to beta and then the derivative of beta with respect to T. Now we've previously shown that d beta dt is the same as minus kBt, the reciprocal of minus kBt squared. Right? So that's d beta dt, and that means I need to take the derivative of this with respect to beta. And so then we can see this as a product, right? Numerator times 1 over the 1 minus the exponential term. So that means we need to use the product rule. And from there, it just becomes algebra. Okay? All right, and then at the end of this, we end up with this being our derivative with respect to T, all right? And then putting this in back into this equation up here, we have to reintroduce our kBt squared and this term here, and that becomes a positive. Okay? All right, so putting that all together, I end up with our heat capacity given by this equation. Okay? All right, so again, this reflects a heat capacity due to translations. This is heat capacity due to rotations. And then this represents heat capacity for vibration. Okay? Right, and then again, just the big picture here, because this relates the change in the energy to a change in temperature. If I increase the temperature, this dictates how translational energies change, how kinetic energies change. This dictates how rotational energies change. And this portion, how the vibrational energies change. Okay? All right, so I want to do a little bit of algebra here. All right, so we ended up with this term, all right? And what we see that we have is an h nu and an h nu. So I can bring those together and make that h nu squared, all right, down here. All right. The other thing is I've got this kb times t squared in the denominator. So what I can do is I can multiply this whole thing by kb over kb. All right. And so that gives me kbt squared in the denominator. So this whole term is squared. And whenever I do this and say, well, I'm going to let it be 1 mole, n becomes n sub a, so I have n kb, which we've previously shown is R. All right? Does that make sense? We good with that? All right. So putting that all together, we have these two relationships to give us the heat capacity per mole for an ideal gas. All right? So it's pretty clear that translation and rotation contributions to the heat capacity are temperature independent. This, however, is temperature dependent. All right? And so that means if you want to know explicitly what the heat capacity is for vibrations, you have to calculate for a given temperature. Make sense? We may do that, but what I'd like to do at the outset is talk about limits. All right? And so the two limits that we'll look at are as T approaches 0 and as T approaches the high temperature limit or infinity. Okay? All right, so if I put 0 in for temperature, this becomes e to the minus this number over 0. That makes this a huge number, right? And it's e to the minus infinity, so that will be equal to e to the minus infinity is 0. So that term goes to 0. That term will go to 0. Right? So I have 0 over 0, and this whole term will go to 0. Right? And so what we can say is that in the limit, as temperature approaches 0, C CV for vibration goes to 0. Okay? All right, so at really, really low temperatures, I won't need to worry about the vibrational contribution to the heat capacity. Okay? All right, we'll get to the high temperature limit in a moment. All right? So up to this point, we've limited our discussion of the application of partition functions to talking about gas phase. All right? So I wanted to take a moment to just talk about an example that works for the solid state. Right? So in this particular model, and this is Einstein's model, we can pretend that a solid exists as a series of harmonic oscillators. All right? And if you think about a solid being, having particles in it in 3 dimensions, that means to describe this, I need a harmonic oscillator for the x direction, the y direction, and the z direction. Does that make sense to everybody? Okay? All right, so given that model, then you can come up with a system partition function that has this form, right? And one of the things that you see is that this exponential over 1 minus the exponential, that's what we've seen for the harmonic oscillator for the diatomic, all right? But now, because I have 3 of them, I have 3. It's raised to the cube power, okay? Makes sense? All right, the only other thing that's shown up in here that we haven't seen before is this U sub 0. That's called the sublimation energy. Right? And the sublimation energy is the energy cost to take my solid at 0 Kelvin and separate it into the particles that make up the solid. Does that make sense? So if this was a water crystal, each of these points would be water molecules. We would take it to 0 degrees and ask how much energy I dump into it to give me water in the gas phase. Make sense? So it's an energy cost to separate solid into particles. So A solid plus U0 to A in the gas phase. Okay? And then this is defined at 0 Kelvin. Okay? All right, so we have a partition function, and then we're going to ask the question, what's the heat capacity of that solid? All right? So we go back to what we've introduced before. The heat capacity, by definition, is the derivative of the energy with respect to T. That means that we need to determine what the energy is. All right? And what we've previously shown is that the energy of an ensemble of systems is going to be given by minus the partial of the derivative of natural log of Q with respect to beta, holding N and V constant. Okay? So that basically says we're going to take this Q, plug it in for this, and solve the derivative. Okay? All right, so what we can do, we can say ln of Q. So this is our Q, all right? And what I'm going to do is I'm going to talk this through so I don't write everything down. We see that this is going to be, this Q is this times this quantity. So that means I can take the natural log of that exponential, right? And those are inverse functions. So the natural log of that first term will become minus beta times U0. We got that? All right. And then next, I've got the natural log of a fraction raised to the 3n. So I can take the natural log of the numerator to 3n minus natural log of the denominator raised to 3n. All right, so that's going to be 3n times the natural log of the numerator, which will be minus beta h nu over 2. Everybody follow that? All right, so I've taken this out in front of the natural log, and it's an inverse function of exponential. It gives me minus beta h nu over 2. All right, and then my last term will be minus 3n times the natural log of 1 minus e to the minus beta h nu. Okay? All right, so now we have expressed this partition function as the natural log of the partition function. Next thing I want to do is take the negative of the derivative with respect to beta. Well, that's going to make that first term go positive. And what's the derivative of beta times the sublimation energy with respect to beta? It's just going to be the sublimation energy, so plus u0. All right? And then the next term, we take the derivative of that with respect to beta, and we see that's a constant times beta, so that's simply going to become plus 3n over 2 h nu. Okay? And then that last term, and we've previously shown what the derivative of the natural log of this is, so we're not going to do it again. All right? So the derivative of that is going to give me 3n h nu e to the minus beta h nu, all divided by 1 minus e to the minus beta h nu. Okay? All right? Okay, and this in turn is equal to the energy of the system. Okay? And again, we can step back and say, well, this is my vibrational contribution to the energy. This is the 0 point energy of vibration. And then this was the energy associated with it being in the solid state. That's the energy needed to pull it apart. Okay? All right, so at this point, all I need to do is take the derivative of that energy with respect to t. All right? So let's talk about the first two terms. What's the derivative of that going to be with respect to t?
0.
That's going to go to 0. And how about that one? 0. Those go to 0. All right? So let me make sure I write that down explicitly. Because there's no temperature in there, all right? And that means what I'm left with is taking the derivative of this with respect to t. Now, one of the things we see is that this is in terms of beta, all right? And so what I can do is say this is the derivative of the energy with respect to beta times d beta dt, okay? And that we've done previously as well, okay? All right, and then we have this 3nh nu, that's a constant, comes out front. We're left with this derivative. And if you go back in the notes, you'll see that we've just previously done that derivative. Okay, so we're not going to do it again. We've shown that it's given by this relationship, and so that means we can plug that in down below. Okay? All right, so this gives us our expression. And if you step back and compare it with what we've seen for the vibrational contribution to heat capacity for our diatomic, this is exactly the same, but with just 3 of them. All right? And that's because I have 3 harmonic oscillators. Okay? Play the same game. I've got this h nu, so I bring out the h nu, square it, multiply numerator and denominator by kb, numerator and denominator by kbt, or kb gives me this, and then introduce Avogadro's number. I have 3r. All right? So I have exactly the same limit for my heat capacity for this that we saw for vibrations previously. All right? And because our model consists only of harmonic oscillators, that's the only contribution that we have to the heat capacity. Okay? All right, before we go further with this, I want to just show this graph from the textbook. This is the heat capacity divided by R as a function of temperature. The little circles correspond to diamond, all right? And then this smooth curve that runs through it is this simple model's heat capacity. And what we can see is that we've got very good agreement between the two of them, all right? So at this point, what I want to do is talk about the high temperature limit. So one of the things that we see is that as temperatures are getting higher, this is approaching 3. Okay? Right? And because this axis is the heat capacity divided by R, that means my high temperature limit is 3R. Make sense? Okay? Well, we want to see where that comes from. All right, so in order for us to do that, what we're going to do is a series expansion, right? So e to the x is given by 1 plus x squared plus x cubed plus etc. All right, in an upcoming math chapter, we'll go ahead and derive this, but for now, we're just going to take it as given, okay? And then we're going to say, if x is small, then x squared and x cubed are going to be much smaller, right? Come on, right? And then we can say that under those circumstances, e to the x will be given by 1 plus x. Okay? All right, and then meshing this with our equation, we're going to say let x be the same as h nu over kb t. Okay? All right, and then we'll step back a moment and say, well, if we're talking about a high temperature limit, that's t's getting very large, that means this whole thing's getting small, and so indeed that will mesh with this identity. Okay? Okay, so from there I can introduce things back into my heat capacity. So my vibrational heat capacity is given by 3R, right? So h nu over kb t squared, that's my x. All right, so now I have my exponential function. I'm going to change that to using the identity 1 plus h nu over kbt. And in my denominator, I'm going to have 1 minus, now I'll do my substitution, 1 minus h nu over kbt, and that whole quantity is squared. All right? So we see that 1 and 1 will cancel to give me 0. In the denominator then, I've got h nu over kbt squared, right? It's a negative times a negative, so it's positive. That cancels with this, okay? Let me just write that out explicitly. So the denominator becomes h nu over kbt squared. Cancels, cancels. Right? And then we have to worry about the numerator. And one of the things we've said is x is much smaller than 1. Therefore, I can replace this with 1. So that's 0, essentially. All right? And what we find is that we have CV equals 3R. Okay? And so what we've shown is that the high temperature limit for heat capacities is going to be R. Low temperature limit 0, high temperature limit R, and in between we have to calculate it using this equation. Okay? All right, let's roll back a little bit. So we can say as t approaches infinity, CV for vibrations approaches R. Okay? We good? All right. Okay, so next up, you may recall that when we introduced the partition function, we said that we can use partition functions to calculate any thermodynamic property. So the next thermodynamic property that we're going to talk about is calculating pressure. Okay? All right, so we're going to step back to the beginning. We think about our ensemble. We have all these systems, same number of molecules, same volume, same temperature. We would expect that the pressure of that whole system, or that we observe experimentally, will be the average of each of those systems in my ensemble. So I can say that the average of my systems in the ensemble in terms of pressure will be given by the summation over all of the possible quantum states of the pressure of the system times the probability of being in a given quantum state. All right? So we're going to introduce something that we're going to show explicitly in Chapter 5. What we can say is that the pressure of a given quantum state is given by the negative of the partial of the energy of the state due to a change in volume, holding n and beta constant. So we're just giving you this now. We will show explicitly where this comes from later. All right? So plugging that in, that says that my average pressure will be given by minus the change in the energy of the quantum state due to a change in the volume, holding n and beta constant. Right? And then I need to multiply it by the probability of being in quantum state J, and we've shown previously that that will be given by our Boltzmann factor, e to the minus beta e sub j, divided by q, our partition function. All right? This is probability of being in a quantum state. This is the energy change for that quantum state, which we know is equivalent to the pressure. I sum over all the quantum states. That will give me my average of my ensemble. Okay? All right. So let's see. So this, I'm going to just rewrite this one more time. So that means that what we're looking for is an expression for the summation J minus change in the energy due to a change in volume, holding n and beta constant times the Boltzmann factor e to the minus beta ej over q. Okay? All right. So this is a summation, and we would prefer to get this into another form, just like we've done whenever we calculate the energy of our ensemble. Right? So we're going to start with our definition of the partition function, the sum of the Boltzmann factors. And we're going to do another math trick. All right? So that means that in this case, what we're going to do is we're going to choose to take the derivative of the natural log of q. All right? So before I go forward, let's just step back a second. What we see is that we have a relationship between energies and volume. So that's going to suggest that we need to take the derivative with respect to the volume. All right? So the partial of the ln of q with respect to volume, holding n and beta constant. Okay? Well, the derivative of the natural log of q with respect to anything will be the reciprocal of q. All right? So we've got the reciprocal of q. All right? So far we're close to this. All right? And then we need to take the derivative of the summation of our Boltzmann factors, e to the minus beta ej, with respect to v, holding n and beta constant. Okay? All right? Just in case didn't catch this, this is 1 over q, and this is the derivative of q with respect to v. Okay? And we know that this is the derivative of a sum. That's the same as a sum of a derivative. Right? Okay? And so that's going to be 1 over q times the summation. Right? So now what I want to do is take the derivative of this exponential term with respect to the volume. Right? Well, we know that's going to give me the exponential back, so I'm going to put that there, e to the minus beta ej, right? So that's the derivative of the exponential with respect to v, all right? And then I need to take the derivative of this with respect to v. Beta has no v in it, right? So that's a constant. And then this we know is a function of v, but we don't know how it depends on v, so it'll just be the derivative with respect to v. Make sense? All right, so it's going to pull out minus beta, the derivative of ej with respect to V, holding n and beta constant. Okay? That makes sense? Beta is a constant, so I can pull that out front. And what I'm left with is the summation of minus the derivative of the energy due to a change in the volume, n and beta constant, e to the minus beta ej over q. All right? And lo and behold, we see this is the same thing as our pressure. Right? Make sense? So this equals beta and therefore what we can say is that our pressure is given by the partial of the ln of q with respect to v holding n beta constant times beta, 1 over beta. Okay? And then we know beta is the reciprocal of kBt, so that tells me that my pressure is kBt times the partial of the natural log of the partition function. Okay? That makes sense? All right, so as long as we have an expression for our partition function, and we do, right? We know what Q is for a monoatomic ideal gas. We know what it is for a diatomic ideal gas. You can plug those in, and you can calculate what the pressure is. And what you will see in the homework is that this yields equations of state, right? So this basically says using partition functions, I can derive equations of state, right? Which gives it a significant amount of power. Okay, we good? All right, so in this next section, what we're going to do is try to see where these relationships. So previously we have Q equals Q to the n over n factorial, right? So we want to see where that comes from, right? And we're going to start with Q for, which ones are we going to do? Independent and indistinguishable, sorry. All right. So independent means, they're not interacting with each other. And then distinguishable means I can tell one particle from the next, right? And I think the way that we're going to do this is in a small group quiz setting. So you can work in groups of up to 4 or 5. Let's see. I'm going to try to get through here without tripping. Are you working with them? Yeah. Okay. If you guys want another one, let me know. Did I give you guys one yet? Could you pass? There you go. Union, we'll give you 2. Sure. All right, so I'd like you guys to start talking this through as a group. I'm going to work it quietly on the board above.
same like idea, yeah, just like instead of one atomic.
All right, so just to make sure we're all on the same page, so we have two energy levels and two particles, right? So the possibilities are I can have both particles in the lower energy state, particle A down, particle B up, particle B down, particle A up, and then both particles in the upper state. Those give rise to 4 different energy terms, right? Because this would be the energy of the system of that first state. This would be the energy of the system in the second state. You can write out an expression for the partition function.
So everyone will have an E, and then yeah, an A and a B. So, and then it's just E2B. Which one has an A and a B? One and one, one and two, two and one.
All right, it looks like time's up. At any rate, if you followed through and carried this out step by step, what you found was that the system partition function is the product of these particle partition functions, all right? Looking at them individually, cross-multiplying, this is identical to what you expanded for the system. That's where we'll pick up on Monday, I guess. Not today. Thanks.